So I have taken a quick survey through my projects, looking for some projects that required or some elements that required modeling of welds in order to perform a finite element analysis, and I didn't find much because it's quite uncommon, it's, at least for my designs. But in general, there are four cases or general cases when you would like or have to model welds to do the finite element analysis. So this would be first, if like in this case you make model of the element including cutoffs or recesses or basically other kinds of preparation of individual parts for welding. In this case there are slots in those plates already pre-designed or designed, so to be cut out while making those elements, and these slots are basically here to apply welds on the later stage. So this is one thing. When you have elements that require welds to be structurally consistent in model, the other basically the other situation is when welds are important for the structural analysis of the element. So when weld is actually taking significant load, and it is important to know how this weld works in the construction. This is one thing, but also the way the weld is done may influence the transfer of forces between the elements. For example, if the weld is not symmetrical or only on one side of the element, or some other not obvious situation occurs, you may want to model welds in case you want to smoothen out the results of the finite element analysis for presentation purposes. If you, for example, have a client that maybe doesn't really like to see points of stress buildup due to sharp edges or some meshing issues with your model, then you probably would like to smoothen all of that out using welds or not welds, it doesn't matter really, because then the results are more smooth and basically maybe more easy to present to the client or other kinds of people that you may want to present your work to. And there is one other thing that came to my mind, but not in the moment. So now this element, for instance, it's designed of, let's say, two side plates, one plate here, and this basically is a connection. There is a pin connection and there is a threaded bar going through this hole, and it takes significant force because it transfers the force from the bar to the pin. And for this purpose I have set up basically a finite element analysis. It's a 1/4, so to reduce the size of the analysis it's 1/4 of the element. So we have some fixture here, half of the pin is cut in half and cut also in half the other way as it's symmetrical in two planes. And here you can see there are two welds that are modeled within the weldment of this element. I think this is the weldment, and there are, if we just for a minute remove this, so this is how this element looks like. So it was not even finished because I do not have all the welds, but in any case I have welds on the half. So I have a groove weld here. What is it? This one. Actually there are two fillet welds. So the weld that fills out this slot, and also two fillet welds on the other side, and two fillet welds here, and two fillet welds on the other side around this edge. And now we will get back with those cuts. So okay, so first cut is with the axis of the bolt, and the second cut is in half. So we have 1/4 of the model actually here, and of course we will apply 1/4 of the force plus appropriate boundary conditions on the cutting planes. And if we go here, of course, and then we'll just remove those. If we examine the contacts, there is a separation contact which is used between the elements that actually can separate. I use this for more close simulation rather than making those contacts, some of them suppressed, as in fact these elements can push against each other, and as a result, and of course, because we have those separations, there are only welds that connect those elements together. As you can see, welds are the only elements that have a bonded constraint, bonded contact. And so we have some results here. So as you can see, I will just make it on the phone. So as you can see, we do not have significant stress buildup in the welds. It should be underformed, but of course it's not. We do not have significant buildup because the most loaded parts are here, but if we just make it, let's see what's happening. And 20 is a little too less. 50. Okay, so if we go to 50, we see that there is a load transfer through the weld itself. We can see how the weld is loaded, and we can see also if there are any build-up, if any stress build-ups in the welds due to how it's assembled. So we can see, of course, here where there is the sharp edge, but it's clear that this comes only from numerical issues because of the elements. You see, this node is the node that is producing this build-up, so it's clearly a numeric thing. We could smoothen this out with an extra bit of work, but there is no point in doing that, as we already see the result in overall. Here is another piece. Okay, so, and also the fourth thing, you would need to model the welds in case your model doesn't stick because the shape of the elements, or maybe this was the first one. So this also is a alignment of basically a part that I needed welds because otherwise there was no contact between these elements, and this is for some reason important in this, or maybe not important, I'm not sure, but in basically the impact of not having this weld would be significant in terms of force transfer. So I decided to go with this weld, although it probably doesn't produce much of the stress because there is there isn't really a connection to the other elements, and it really doesn't matter so much. So, and this is another sample of that. So if we go out, there are welds here because actually these elements do not touch. So if I just let's say hide them, is it possible? No. So there is a gap because those plates are cut a little short, but otherwise I didn't model welds to fill those gaps between those elements because it's not really necessary. Also here, although this is just touching, but going with the bonded contact, it's fully enough for this model. Of course, in the end there are fillet welds here and also there, so so actually the area of the weld is made bigger than the area of the plate itself, but as long as it is not strictly necessary to model welds, personally I try to avoid them for obvious reasons. It takes longer and longer uh, to to calculate, and as we can see, since the stress level in overall is not high, there is no point in making this analysis more complicated than it needs to be. We also, of course, see that there are stress buildups here because, of course, again, because of the meshing, this point really does not stick to anything. So of course we have the stress buildup here, but as you can see, this buildup is only in one element away from the node. Here is more significant because of course this plate takes most of the load here and gets it there. So this is here, but assuming we will have it welded, we will have even more cross section here, and there is no real danger for any for this part. Actually, all of those parts that I have just showed you have been produced, used on site, and basically they are actual designs that have been executed. And this is another example of the thing of the element that requires welds to be modeled, as they are actually necessary for this element to exist, as this is basically key, because this was welded of two elements. But in this case, the weld is not done by weld itself, but the weld is done by a separate part that's basically a separate part, a model that represents the welds. It fills gaps between the elements that are being, let's say, parts of this, and then these welds are machined after they are placed in the actual model. So in the end, this looks like that. And if we go to stress analysis, of course it's half. We do not have results here. I think we even do not have a mesh here. Okay, actually we have a mesh, but we do not have results. I'm not sure we have any loads. Yeah, there is a node. There is some question. So let's run it. There are pending geometry. I'll just continue. Run. And since this weld is modeled as a separate body, separate parts, we of course will be able to have it separate in results. So if we now, let's say, hide if we hide the rest, we will only get the weld itself, and we can examine the stress in the weld itself. I think if we just go there, so we can see that the maximum stress in this element is 292, which is of course some numerical peak somewhere. Okay, so here, because of the modeling simplifications I did while doing it. So but overall, if we just see, overall this is of course a numerical thing because of this thin edge here that represents let's say some discontinuity in the material. So overall, I was trying to look for other assemblies that I used for finite element analysis that basically would use welds, but really I didn't find much. Even this one that is quite complicated, but it's done without weds, because it's easy enough to assume bonded connections here, and they are close enough for how this will be after it's welded, so there is no point in bothering with modeling welds themselves. So basically this is, in terms of using welds, I think this model here is is making the most use of welds as a weldman and inventor, as these welds come from weldmen and they are here. But as you can see here, they are modeled without any chamfers on the ends or some fillets or whatever. Probably they will not be as sharp in the real life, and this is obvious, but if you model it like that, it's perfectly fine.